All right, folks, I think it's time. Welcome back. Hope you had a good weekend. So, at the end last time, we were talking about converting a grammar into a stack machine. And I want to do just a real quick couple more examples of that. Grammar to a stack machine. Right? As I mentioned last time, I don't know if you've checked out the homework yet. The homework involves writing a bunch of stack machines. You may find that this is an easy way to create a stack machine is first make a grammar and then convert it into a stack machine. I find it a lot easier to make a grammar than a stack machine. But anyway, the idea is if I have a production, say x goes to y in the grammar, this makes a rule in the stack machine of read epsilon, pop x, push y. And then we also have rules that say things like A epsilon, yeah, that's right, or B epsilon. Each letter gets its own transition like that. And like for every letter, and we always get epsilon s epsilon for the starting state, for the starting grammar symbol. Gives you a rule in a stack machine like that. All right, so this is sort of one type of rule, and then these types of rules, and then that one special rule. Right? Every grammar production turns into rules like this. They're epsilon read rules. Every letter turns into rules like this. And then whatever the starting grammar symbol is turns into this rule. All right, so for example, as a simple example here, we did one at the end last time. I'm just trying to refresh our memory. So something like S goes to ASB or epsilon. All right, this is the grammar for A to the N, B to the N, in case you care. How would I turn that into a stack machine? According to this construction, so I go read, pop, push. Okay, first of all, we have S goes to ASB, which according to the strategy I wrote up there, looks like this, right? This is like one of these, right? Up here I said if you have X going to Y, then you get epsilon X, Y. In this case, I have S going to ASB. And so I get epsilon S, ASB. Sorry, I'm now realizing I shouldn't have written this. Can I just scribble this out? This is not true. I was confusing this with something else. I'm not sure. Yeah, this is something having to do with converting a regular language or an NFA into a stack machine. Yeah, sorry about that. Converting an NFA into a stack machine gets you things like that. This rule, what I just scribbled out, will naturally happen in this example, although it's not because of a special rule. It's just because there's another production. S goes to epsilon, right? And how do I translate S goes to epsilon in this way? It's just going to look like epsilon. Epsilon S epsilon. All right? And those are the two productions. So this one came from S goes to ASB. And this one came from S goes to epsilon, right? And then I also have these two rules for each letter. I get A epsilon, read A, pop A, and I also get read B, pop B, epsilon. And that's it. This is the whole stack machine, right? I'm looking at my, all right, forget it. Okay, any questions about that? This is the process. It's not hard to do. You just gotta keep it straight. Unlike I just did a few moments ago. Okay, I would like you all to try. Let's try make a stack machine out of this. This grammar has like one big line in it. S goes to ASC or AS or BS or epsilon. So your job, make a stack machine. For this language, and and then show a stack derivation for the string A, B, A, C, C. All right? So remember that your answer for that part should look like A, B, A, C, C, comma, S on the stack, and then you do a bunch of steps, eventually ending with epsilon, epsilon, right? See what you think. So first write the stack rules, and then see if you can write out the derivation for that string right there. When it comes to writing your derivation, your strategy should be, I would suggest first write a grammar derivation, and then try to copy the same steps that you used from the grammar in the same order on your step. I'll give you another minute, and then we'll talk about it. All right, let's chat about this. So I wrote my stack machine first of all. As I was going around, I saw everybody got this. You should have seven rules total. 4 of them come from just translating each of these 4 productions. Those are the first 4 there. They're all epsilon reads. And then we also have AA epsilon, BB epsilon, CC epsilon. Great. Now, to derive the string on the stack machine, my suggestion to you was first write down a grammar derivation, which I did here, and then try to copy those same steps in the same order. So the first step that I did was S goes to ASC. And so I'm going to do the corresponding step in my stack machine. Maybe just for clarity, I'll put numbers here. These are my numbers. I don't know if your numbers are the same as mine. Okay, but anyway, I'm going to do rule number 1 first because in the grammar derivation, the first step was S goes to ASC. So I'm going to do the corresponding stack step. So what happens is an epsilon read, so I do not modify the string at the beginning here, and then pop S and replace it with ASC, so it looks like that, right? Every step that you do here is going to cause some extra stuff to go on the front of the stack, which you should pop off using one of these rules, 5, 6, 7. So I'm going to use rule 5 to get rid of this A. And the effective rule 5 is basically to erase this A over here and also this A over here. So I'm going to go rule 5 here. Wipes out the A at the beginning and also pops the A off the stack like that. And now I continue with my next grammar step. So the next grammar step was the S goes to BS. That is rule number 3 on the stack machine. So I'm doing rule 3. Don't change the string, but S goes to BS means that. All right? And then I do the read B, pop B rule to get rid of the B's. It becomes AACC and then SC. That was rule 6. Any questions about any of this? I hope everybody's following along. I think you are. Okay, next, I'm ready to do another grammar step because I have the S on the front of the stack again. So I just did this one. The next step was S goes to AS. So I do rule number 2, AACC, ASC. Then I pop the A's, that's rule 5, ACC, SC. All right, next grammar rule is S goes to AS again. Okay, that's rule number, what is it? Number 2, ACC, ASC. Then pop the A's again. That's rule 5. CCSC. And then my last grammar step, I think, was... Did I mess something up? I should have made another C. Yeah, right there. I did S goes to ASC here. Yeah. Okay, so I should have 2 C's here. I feel good about that. Then the last grammar step that I did here was S goes to epsilon, which is rule 4. That just pops the S off. And then I do rule 7 twice to get rid of the C's. All right. There's a lot to write here, but if you know the proper strategy, you can get down to the epsilon.
I said all the 3 epsilons, and then I did it differently, but not the same way. I did all the 3 epsilons first, and then I ended with until I got to like BAA, C, BAA, C, and then just did like all.
Then you did all those.
Yeah.
I'm not sure that's legal because, like right here, for instance, you did rule number 1 again immediately after this.
I think I did 3. Like,
Okay, yeah, rules. That's what I meant. But your rule 3 is not legal at this point because rule 3 requires S on the top of the stack, and the S here is in the middle.
I think it only popped because I was on the side.
Yes, yeah. Because of the way the stack works, when you pop, that removes the thing on the leftmost end of the stack, which is why you actually have to kind of intersperse the steps within one another. Yep.
If your grammar derivation is different, that's fine.
Yeah, sure. If you wrote a different grammar derivation, then that would translate into different steps down here. So, yeah. No problem. All right. Anything else to say? No. Great. So this is the way to translate a grammar into a stack machine. Like I said before, this may be the way you want to approach most of the homework problems because, in my opinion, it's pretty hard to write a stack machine, but much easier, to me at least, to write a grammar and then convert it. Although I don't know if you saw the assignment. In the first problem, I want to force you to write it as a stack machine. The others, I said, you can do however you like. All right. Let's talk about, as our main topic for today, perhaps, how about going the other way around? Can you go from a stack machine back to a grammar? All right. This was about grammar to a stack machine. Can we go other way around? How about stack machine converting into a grammar? In fact, there is a procedure for that also. It's completely different. Ordinarily a stack machine will not have like mostly epsilon transitions and then these special letter transitions, right? Usually a stack machine is just going to have, you can't really predict what it's going to have, right? So what I'm about to describe is a little mysterious why it works, but let's talk about how to do it first of all, and then we'll talk about why you should believe that this works. So it's again a very simple procedure to do. So here's how we do it. I have to tell you, you translate line by line. So each rule on the stack machine, read, pop, push, translates directly into a grammar production. And here's how it works. If you have a read, pop, push, and let's just say it says X, Y, Z, a line like this translates into the grammar production. Here it is. Y goes to X, Z. If you do that, you will get a grammar that's equivalent to this stack machine. It's that simple. We need to talk quite a bit about why that works, but let's just do an example first of all, and maybe you'll be convinced it works. Although to me, it's even after you see an example, it's still a little mysterious. But let's try it out. So, for example, how about here is an example stack machine. This was all X on A's and B's, such that the number of A's is equal to the number of B's. We did this example a few times ago. The strategy for this, if you recall, was every time you see an A, you put like a big X on the stack. And if you already had some extra A's and you see a B, you remove one of the X's from the stack. If you have extra B's, you write a Y onto the stack and then remove those when you read A's. I don't know if you remember this example, but I don't remember exactly what day we did this on, but this was one of our first examples of a stack machine. Here's what the rules were. So remember, if you see extra A's, they come out as X on the stack. So every X represents, I have an extra A, like more A's than B's. And each X represents one extra A. And then if you see a B, and it was an S, you push YS. If you see S, that means they're like equals. There are no X's or Y's. And if you're reading an extra B, then you should push a Y. And then if you see A and there's an X on top, that means you already had extra A's. Then you should replace it with XX, because you just got yet another extra A. But if you had a Y on top, then you replace it with epsilon. That is to say, if I read Y in a situation when I already had an extra B, sorry, if I read A in a situation where I had an extra B, they should kind of cancel out each other. They should equalize, right? And then similarly for B. So if it's BX, then we push epsilon because the B kind of cancels the X. If it's B and Y, we push two Y's. And then this was a special thing to allow you to finish at the end. In this particular stack machine, the S always sits on the bottom of the stack, like furthest to the right is the S. And if you finish with just the S on the stack, that means when you got to the end, there were no extra A's and also no extra B's. It was equalized. All right, so anyway, this was the stack machine. We are going to create a grammar. So all of this, you just translate line by line in the way that I just described. And it says, remember, when you see XYZ, you go Y goes to XZ. So this one goes S, I went blue. S goes to AXS. You feel me? This is kind of weird, but it works. The next one will say S goes to BYS, right? And you just keep doing them like that. Next one goes X goes to AXX, all right? I'm going to do them all. Y goes to, I guess, just A followed by epsilon, but that's just A. X goes to B. This one says Y goes to BYY. And the last one says S goes to epsilon. All right? This is my grammar. And, of course, we wouldn't ordinarily write it this way. So you can kind of condense this or simplify, I guess. Just to say S goes to AXS or BYS or epsilon. I put together all the ones with the S. And then X goes to AXX or B. Y goes to A or BYY. Right? It's the same thing, but I kind of condensed the different productions. All right? This is the grammar. I want to see if we can just do an example here. So let's try the string ABBA. ABBA. This one does have the same number of A's and B's in it, and so it should be possible to derive that using the grammar that you see on the left there. Now this is kind of a complicated grammar, and it's maybe not obvious how you could make ABBA with that. But the strategy, it turns out, just like the ones that we were doing a few minutes ago, the way to do this is first write the stack derivation and then translate that into the grammar derivation sort of step by step, and it'll work out great. So I'm going to, so my real job is to try the ABBA on the grammar. But in order to do that, I'm going to do it on the stack machine first and then translate step by step. So first, I'll do it on the stack machine. On Stack'em, I got to do ABBA, comma S. And now, can I keep it on the screen at the same time? No, not really. Maybe, would you mind if I just do it down here? ABBA, comma S, right? What should I do first? Now, on the stack machine, you don't have a lot of choices. Actually, I don't think you really have any choices. Every step should be dictated by what you see on the stack. S is on top of the stack. I must do the top one, like rule number 1 here. I read the A, so that goes away. I end up with BBA, comma XS. Right? I did the first rule there. Now I have a B on the front of the string and an X on the top of the stack. I think the only choice is to do this line here, bx epsilon. There's no other option that we could do at this point. Anyone want to say, can you shout it out? What remains when we do that step? BA, comma, S. Yeah, great. We read the first B, so that goes away, and then on the stack, the X gets popped and replaced by epsilon, which is nothing. Okay, next I have B on the string, S on the stack. I have to do this line, BS, YS. So it becomes, play with me, all right. B goes away, S becomes YS. All right, and then I read A, pop Y, push epsilon. It becomes epsilon S, and then the last line there gives me pop F. Read epsilon, pop S, push epsilon. Those are two epsilons at the end. Those are some pretty sloppy epsilons. I'm going to do it better because my hand's on the end of the screen. All right, this is the stack derivation. Can we translate this into a grammar derivation? That's why I did that all. On the grammar, I'm going to try to do the same steps in the same order, all right? I begin with, the first step I did was from rule number 1 here, which corresponds to this rule, S goes to AXS. So that's how I'm going to begin. I have to start with S on the grammar. A, big X, S, right? I'm being a good boy and using the proper arrows. Remember, on a stack machine, I don't really care about this, but on a stack machine, they look like this with the bar on the left side. And in the grammar, they look like this with the double extra thick arrows, thick with 2 C's. Because I know that's how the young people write that word these days. All right. Which step on the grammar should I do next? You look back here on the stack machine. The next step that I did was read B, pop X, push epsilon. That's this line, which means I should do this line on the grammar next. X goes to B. Okay. That's easy enough. All right. Next. My next step was here, right? BAS became AYS. That was a read B, pop S, push YS. So that's what I'm going to do next. S goes to BYS. My S goes to BYS. A, B, B, Y, S. Abby's. All right? The next step was this one here. Read B, pop S, push Y. That's... What? Now, this is the one I just did, isn't it? Next is this. AYS goes to epsilon S. So I read A, pop Y, push epsilon. That's this line, which is Y goes to A. And then finally, I do the S goes to epsilon line. Now, this one, maybe you could have figured out how to do this grammar derivation without going step by step like that. But in general, you're going to want to have something to look at because this grammar, like in general, can end up being quite complicated and hard, in my opinion, hard to see what step to do from one to the next. All right. Any questions about that? First of all, I want to talk a little bit about. Actually, I want you guys to try one, and then we'll talk about why this works. So I'm going to write another stack machine here. Your job is to convert this into a grammar. Maybe I'll mention before going on, it is possible to simplify. Sometimes it's possible to simplify even more than this. What I did here, first of all, was not much of a simplification. I just gathered things together. But sometimes when you look at this, you'll see productions which can be rewritten in a simpler way. Although this, I'm not sure. When I look at this, to be honest, this doesn't really look like anything to me. It looks like a bunch of nonsense. It's hard for me to wrap my mind around how the grammar works. Anyway, okay, here's one I would like you to convert into a grammar. So it says read A, pop S, push. I'm using zeros on the stack. Can you handle it? Yes. Read B, pop 0, push epsilon, and then I have epsilon, S, epsilon. All right? So I would like you to convert to a grammar. And on your grammar, derive the string A, B, B, B. All right, see what you think. Let's try and do this in 10 minutes, and then we'll have 10 minutes to explain why it works. That'll do it. No, it just helps the idea. Okay. I'm going to start doing it. Don't look if you don't want to support it. Is anyone able to derive that string? Everybody?
I can't get this stuff.
Oh, so maybe, yeah, sorry, I meant 4 B's. That,
That was not.
I think with 3 B's it's not possible. Sorry about that. I just looked at my paper again. 4 B's. All right, are we ready to talk about it? I think pretty much everybody wrote the grammar down correctly up here. This is the grammar. Just translate, I can see very well, huh? You just translate directly from the stack machine. All right, that's the grammar. Now, in order to derive my string using the grammar rules, first I'm going to do it on the stack machine, and then I'm going to just be able to copy those steps. Now, some people are asking me, do you really have to do that stack thing? Can you just do it directly from the grammar? The answer is, yeah, you could just do it directly from the grammar if you are able to sort of visualize in your mind how to use this grammar. Sometimes this grammar can be very weird and not at all easy to work with in your head. But anyway, this is how I would derive the thing on the stack machine. Translating those steps into a grammar would look like, okay, I begin with S. And then the first step I did was the top line, so I go S goes to A00S. What's the next step you did? Anybody get this? Get this one? Yeah, what'd you do next?
A, pop 0. Wait, sorry. This one. A, then 4 zeros and an S.
A, 4 zeros and then an S. Yeah, so that was this. Which rule is that? I guess we did this rule. 0 goes to A000, right on the first 0. Yeah. Great. Okay. And then the next, so that corresponds to this read 0, read A, pop 0, push 0, 0, 0. That was the second rule. And then from here to here, I read B, pop 0, push epsilon. That is the same as 0 goes to B. So I send the first 0 to B. Actually, I'm going to do that 4 times, right? In fact, this is easy. Maybe this one is not so hard to do just by looking at the grammar. I'm going to turn each of those zeros into B. ABB 00S. ABBB 0S. AB. Sorry, I lost the A. AA. B, 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 S, and then finally get rid of the S. A, A, B, 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 B. The end. All right, this is the grammar derivation. Great. Anybody have any questions about that? It's not really a hard process. You just have to remember how to do it. Now, I'm going to talk about why does it work? Why should you believe that the stack machine is equivalent to this grammar derivation? In my opinion, it's a little mysterious. I'm going to try to explain, check out, if you will, what, let's use this as an example. What does this thing look like from step to step in the grammar derivation? You will notice that from step to step, I am, one letter at a time, I am creating the string that I'm looking for, right? What I'm looking for is AA, BB, BB, right? And you see that string is growing one letter at a time from my, as I do the grammar derivation. That actually is kind of complementary to what's happening on the stack machine. This word or this string is shrinking one letter at a time, right? Until it becomes epsilon. But it's the same, they're kind of inverse or complementary processes, right? As in the stack derivation, the string shrinks letter by letter. In the grammar derivation, the string grows letter by letter. And what do you see sort of right next to it? Can anyone say, so looking at the grammar derivation, the things which I did not underline, can you see any relationship between those and other stuff that you see, like in the stack derivation? The things that I did not underline? Yeah, actually, the things that I did not underline are equal to the stack every time, right? So like, if I were to make them, say, green, this guy, they're the same, right? So what you see here in the grammar derivation, so our grammar derivation, I'm trying to explain to you why these are actually equivalent under the hood. I mean, they look kind of crazy, but they are actually doing the same thing. Our grammar derivation always looks like, you can kind of break it into two parts. There's like the red part and the green part, as I color coded them above, right? And the red part is the string red so far, right? As you do in the stack derivation, the string disappears one letter at a time. But as you can see, when you do the same thing in the grammar, the string is appearing one letter at a time. So what you see is how much of the string we have already read so far as we're going. And then the green part is just the stack from step to step. Right? So what you see at the beginning is the string which has been read so far, and then it's followed by the green part, which always represents the stack. And where these things change from one step to the next as you go through the grammar, the change only occurs like right in the middle, like where the red and the green meet. That's where it changes from one step to the next. It doesn't change all the way on the right end or all the way on the left end. So maybe I'll just say each step changes in the middle there. Here, right? Each step in the grammar, we're not changing the ends of these things. It's just right in the middle where it gets modified each time. All right? So that means, if we use a rule like read, pop, push. If we use a rule like this, read X, pop Y, push Z. Now, in the stack machine, this has the effect of removing X from the front of the string, but on the grammar, really, it should be inserting the X on the X on the rightmost end of this red part. Okay, so if we use a rule like this on the grammar, we should. What about, maybe I'll say first of all, what happens to the green part in the grammar derivation? The stack, we should remove Y from that part and replace it with Z, right? So on the grammar, we should remove Y from the green part and replace it with Z. From the left end of the green part, I mean. And because we read the X, we should insert an X on the rightmost end of the red part, right? Because I read an X in this step. If I read an X, that should stick a new X on the end of the red part here. So we should remove Y from the green part. When I say from the green part, I mean the left side. Sorry, I said this out loud. I should have written it in there. We remove Y from the left side of the green part, replace it with Z, and add X to the right of the red part. Sorry, I'm off the screen here. Off the easy. All right. The effect is to remove a y from the left side of the green part, replace it with a z, and also add an x onto the right side of the red part. What that means is, what we're looking at is a situation where we had a y here, and the effect of this step is we kill this y, we stick a new x here, and we replace the y with a z. That, as a grammar step, it looks like y is being substituted with xz. And that's why this trick works. This is a long explanation just to explain to you why. This is the same as a grammar step. Y goes to xz, which is the whole basis for this trick, for translating a stack machine. So, in conclusion, a stack rule like this translates into a grammar rule like this. All right? I would say just memorize that. And if you ever find yourself wondering, why does that work? It's because of all this that I just said, although it may not be worth trying to think it through every time. For me, I don't really try and think it through every time. I just remember y goes to xz. All right. I think that'll do it. We got a few more minutes, but I don't want to get into it. So I will see you all tomorrow. Check out that homework.
I just